Alright, so I'm back. So essentially we stopped because the video was getting too long, but now we in a place where we can say, okay, fantastic. So what we've learned about interpreting these eigenvectors now, that they're essentially meaning about nodal displacements. This is just following basic linear algebra logic through here. Okay, but really powerful, this idea that we can now interpret them. Now, if that's the case, okay, what we can do is we can say these eigenvectors are really the nodal displacements. Okay, so if that's the case, I can then say, let's look at the deformed and undeformed displacements, okay, for different modes that I choose. So let's choose eigenvector number 0. So we've computed these eigenvectors, and eigenvector, let's go back, see eigenvector, the first eigenvector was associated with the largest value here, second largest, second, and the third one was the lowest one. So this is the column index 2, column index 1, column index 0. So let's look at column index 0. What's going on? So let's just do that one, and if I plot that, I see, ooh, it did not run all these cells. That's the first thing that I see. Okay, that I got here without running all these things. And what I'm just looking at here is the following. The red dots are the regional coordinates, okay? And these green dots are my deformed coordinates. And what I'm seeing here is this node was here is now there. This one that was here is now there. And this one that was here was essentially there. So what I can see is things moved out, yeah? So this node went there, this node went there. And we can even multiply just with some scaling factor if we want to make it a little bit less, the displacement. So we can multiply it by, let's put in here a scale factor, SF, and say 0.2. If I don't want to take the full displacement vectors, displacement would rather scale a little bit so we can get a better idea what's going on. And I can see if I multiply by the scaling factor, we see essentially, just see what is going on here. If it was 1.0, it would be what we had. If I multiply by 0.1, let's just make sure we seeing correctly. Okay. So if I look at this, so this is maybe going to give us a better view. If I just take a little bit of that eigenvector, not the whole thing, so we just can see it very clearly. This node moved here. This node moved here, and it looks like they moved the same amount. So it looks like these two nodes sort of just moved this from here to here, and this other eigenvalue is really the mid-side node that moved out. So it looks like there was a rigid body motion of these two outer nodes. They just moved, they translated the same amount to the left. Okay, but this middle node, what we see here, is the one that moved away from its center node. So that one moves quite a bit to the right, and this is associated with lots of strain. Let me run it. But this is essentially something I can imagine if I wanted to do this to a bar. Just like, let's take a bar and almost just rigid body motion the two outside nodes, but take the inside of that bar and move it quite a bit towards one side. That will take quite a lot of energy. Okay, so that is what we see from this eigenvector, that deformation mode. The next one I can look at and say, the next one, the center one stays the same. Okay, but the outside. So this red node moves to the left and this one to the right. So that's sort of uniaxial tension. That's exactly uniaxial tension. Can you see that? That is a tensile mode. To say the red nodes moved out towards the side, putting us under tension, and the middle just stayed where it was. And that is equivalent to a uniaxial tension over the cross of the right one, where we're pulling with a force to the right and to the left, such that we put the bar into uniaxial tension. That is a beautiful thing. Okay, and now we can think of the last one. This is the one with the 0 eigenvalue. And remember what I said to you, that column, the values were the same in that eigenvector. And now we can see that if the values are the same, this node moves there, this one there, this is just a rigid body motion. And a rigid body motion, yeah, is something that really doesn't add stiffness. It's got nothing to do with the stiffness of the material. And this is why we see essentially 0 eigenvalue associated with that. Okay, because essentially this is just a deformation that is related to, that's a deformation that's really just related towards a rigid body motion. There's not going to be any stresses, no reaction forces forming because of anything like this. If you go back to the previous one, you can imagine that to be able to do this, there needs to be some loading applied to this. So there's a non-zero strain energy associated here, and for this one, there's a non-zero strain energy associated here. But the strain energy here is going to be 0. Yeah, because of rigid body motion. But just move a bar. Ask you what is the strain energy in that bar? It is a complete rigid body motion. There's no strain energy that's stored in that bar. Okay, that is important to understand. So already we are getting an idea that these eigenvectors and possibly these eigenvalues are somehow related towards strain energy. Okay, so this is what we see, and now we can go and say, all right, what I want you to do is, let's look at the mode. Let's take the, and to show you that it's related, this eigenvalue related to strain energy, let's compute strain energy. We know now the strain energy you can compute as a half V transpose KV, okay, or a half Q transpose KQ. That's sort of what we had in the notes, but what it means is this is our formula for computing strain energy. So this KQ is the force, yeah, and this half Q half V is essentially, if I were to integrate this force over the displacement, I get this formula, and that's my strain energy formula. Okay, so that's essentially what we have. So that is strain energy in the system, and then I'm plotting just the eigenvalue associated with that mode. And what we see is that the strain energy is 168, and then how, whatever, this is how many, 3, 6, so 168, let's say megajoules, yeah, and then I see that my eigenvalue is twice that. If I take this value multiplied by 2, I get to this. So the relationship it seems between the eigenvalue and strain energy is factor 2. Let's look at that. Look again, that's 42, that's 44, 84. So that's essentially, we can see that relationship. And if I make it 3, this is the third one, then I say, oh, the strain energy is 0, and this Lagrange multiplier is 0. So both of them are 0. So that's stunning. This is telling us clearly that the relationship between eigenvalue and eigenvector is that the eigenvalue is twice twice the strain energy. Now we have physical interpretation to the eigenvalue. Stunning. The eigenvector is the nodal displacements associated with deformations that we can have, and you can, any solution, write as a linear combination of that, and the eigenvalues are the amount of strain energy associated. This is critical to understand. This is going to give us lots of insight later on in this course to help us to interpret why certain elements behave the way they do. So one thing that is really important, fun elements, when it comes to thinking about structural solid mechanics and finite elements in general, the K matrix is really, really, really important to think of the K matrix in terms of eigenvectors and eigenvalues, because they really give us all the insight of what this thing can do. Okay, that is important to understand. Because the eigenvectors and eigenvalues of the stiffness matrix tells us what are the ways we can deform, and essentially what are the associated strain with those deformations. And we go back here and we ask ourselves, what is this deformation? So it tells us we can have something where essentially the mid-side node moves. Okay, that's one thing that this thing can do. We can have something that is uniaxial tension, or it can be also compression. If I were to multiply by a negative, it will be compression. So tension, compression, the mid-side node can move. That's what we have now. And the third thing that this element can do is the rigid body motion stuff, to say, you know what, I'm not going to associate energy towards this if I have rigid body motion. Beautiful. Now we have really good understanding of what's going on. Okay. And now obviously I can make up my own strain energy and go and compute what is the work done if I were to go and solve for a system. Okay. So an example here is, for instance, to say this is the PDF handwritten notes. If I were to take those displacements that we computed for the applied loading that we had, I can say the work done by the force is essentially a half QF, Q transpose F. That is the work done. And then essentially I can say, well, we know F we can write also as KQ. And so that is then a half Q KQ. That's really what the strain energy is then. Okay, so that is and what we're seeing is the force, the work done by the force here on the structure is the same as the strain energy stored in the structure, because we don't have any damping in the structure. There's no losses or anything like that. And so these two are exactly the same. So the work that we do in the structure gets stored as strain energy in the structure. Okay, and that is really what we see here. And this must hold. If this doesn't hold, then there's no conservation of energy. So this is really important, just to see that even just from our first year physics point of view, everything that we're doing are making complete sense when you just think of it from an energy argument. What is the work that we do versus the energy that we store? And so beautiful, we see that they are the same. Okay, this hopefully will give you a good idea of an insight into interpreting finite elements beyond just looking at stuff and matrices and just vectors for just as numbers, but to say, but they really have beautiful meaning, and really we can interpret them beautifully within terms of physics. And a vehicle behind that is the eigenvectors and eigenvalues. This is why this notebook is also called Eigenvalues and Eigenvectors. That's why it plays such an important role. Okay, I'm going to stop this video here, and this is sort of hopefully will get you going on the tutorial. Thank you.